Now that we know how to model the way fluence is set up inside of an infinite tissue geometry, we've got to figure out how to write the expression for light distribution inside of a semi-infinite geometry, which is to say a tissue region that has a boundary, say, with air. This is kind of complicated, so hang on. At the air tissue boundary, we can think about that light distribution we've talked about before, this angular distribution of light. We called it lowercase u. Remember, it's a function of where you are, vector r, what the direction is of the light you're considering, omega hat, and possibly also of time. And if we go now up to the boundary and we consider a point essentially right at the boundary, if we think about this U distribution, we can think about the light heading upward and going out of the tissue. And I'll draw it something like this. I'll draw 3 representative arrows. Now we think about the relationship that this has to have the light that's going upward from this point and the light that's coming downward from this point. Well, the only light that's going to be coming downward from this point are the reflections of these rays that were going upwards. So bear with me for a second. The light that's going in this sort of flattish direction is probably going to totally internally reflect off of this tissue air interface. So we're going to have about the same so we get a reflection like that. But these other ones are going to transmit through a Fresnel coefficient less than 1. And so they might reflect a smaller fraction of what was there. So we end up getting a distribution of something like this. Strongest in the upward direction, smaller in the downward direction, and somewhat matching actually right about at the boundary. So a pretty smooth distribution here. And we could reflect this around the other way. So here's our distribution we've got there. Now, the way we will formally manage within the diffusion approximation, which has thrown away a lot of terms, the way we can write a relationship between the upward and the downward component here is to integrate over the upward 2 pi solid angle in the upward direction. That's the upward going value of u at all these points. And then we can also integrate over what I'll call the negative 2 pi steradians, the downward direction of this light distribution. So we end up having 2 rules that relate the upward half to the lower half. So what are our rules? Well, the first rule isn't about the upward and lower half. The first rule is just about the fact that we always have to model u in the diffusion approximation as this distribution being an isotropic term plus a cosine dependent term. So we're writing something always as a U, capital U, and a capital F for flux. And there's a relationship between the flux and the energy distribution. And I'll just remind you what that is. The flux is minus diffusion coefficient times the gradient of capital U, where both of these terms have dependences of R and T. So that's just a rule about diffusion, which is something that got us here. But we also have this relationship about the upper half hemisphere and the lower half. So that was the first rule. Our second rule is that if we integrate over all the downward going light, I'm going to write that very conceptually. If we integrate over that negative 2 pi direction, and we integrate over all the values of this energy density per unit steradian, U, and we associate each one of these arrows, we associate an amount U in that direction. So I'm going to just write the angular dependence. So for each angular direction U, I've got that, and now I'm going to associate that quantity. I'm going to actually write that vector direction, and I'm going to dot it into the downward direction from the normal. So I'm now going to keep track of the surface normal. That would be a unit vector in the upward direction, surface normal. And if I write the opposite direction here, I can have negative n hat, the inward going surface normal. So I dot this into the minus n hat, and I'm going to integrate that over all solid angles. So although this looks very mathy, all I'm doing is associating each one of these rays with a direction, and then dot producting it with the downward normal. So I'm sort of taking the negative z component of each one of these downward going arrows. And the assertion that we make here is that in all cases, the downward component is the Fresnel reflection of the corresponding upward component. We're going to do a sum over all the positive 2 pi directions. And I'm going to do the same thing that the book does and pull out an overall Fresnel reflection coefficient, which sort of averages over the reflection coefficients for all of these different angles. So it's going to be the same sort of integral here we're going to associate with all the upward directions, various directions omega hat. Now they're in the upper hemisphere. Once again, I'm going to multiply them by a vector direction to make that these rays actually be vectors. And I'm going to dot them into the positive n hat vector. So now I'm taking the positive z components of these upward going vectors, and I'm going to integrate that over all solid angle. The overall result of this is just a mathematical way, you'll see something like it in the book, saying that the downward going light is equal to the Fresnel reflection of the upward going light, summing that over all upward directions and all lower directions respectively. The net result of this is that since the U distribution is composed of a capital U and an F term, we now have two relationships, 1 and 2, relating F to U, and that at the end of the day gives us a relationship between U and the normal derivative of U, the derivative of U in the direction of the normal. Pretty mathy, but here's the result. When you go through all of this, you get the following result. The particular relationship that's prescribed at this boundary between U and its derivative with respect to the normal is this. The normal derivative of U for any surface point R sub s. So R sub s locates any point on the surface. That normal derivative is equal to the following quantity. Negative speed of light in the medium over 2 times a constant A that I'll mention in a second, and the diffusion coefficient D times U itself. Again, for any point R sub s located at the surface. So that's the key result that comes out of doing the math. This is the boundary condition for this semi-infinite geometry. So this term on the left is the rate of change in the n hat direction. If I show you for a second what the virtual tissue simulator says, here's a fluence distribution, an energy distribution that you set up inside of the tissue, and you can see what we're talking about is as you move closer to the surface, the energy density is decreasing. So motion in this direction is that helps me calculate the derivative with respect to the n direction, the surface normal. And you notice that anywhere I do that calculation, I have a decrease in the fluence as I approach the surface. So I've got my change in energy density as I approach the surface, and you'll notice that there's a negative sign, so it's decreasing. And the other thing that you see here is this quantity A. I will just flag for you over here. What does A equal? It's a quantity that equals 1 for no reflection. So if there's index matching at the surface, then the light sails through from the tissue to another medium with the same refractive index as tissue. So then that quantity would simply be 1. If it was a mirror at the surface, as the book tells you, that would be it will be infinity for total reflecting surface instead of no reflection. You have total reflection, and in the middle, just to give you this as a reference point, a value of about 2.9 is the value that you get for when n of tissue equals 1.4. And the refractive index above is air. So that's a good number to throw in, about 2.9 for actual tissue problems. The rest of this tutorial, we've got to figure out what to do with this boundary condition. And we are going to work on something called the extrapolated boundary. Let me write that out for you. Okay, the extrapolated boundary, if you look in our course's textbook, if you have that, that's figure 9.8. And by the way, this over here was equation 9.48. So the extrapolated boundary, if we go back to that picture over here, if I'm moving upwards here and the energy density is getting less and less and less, I can ask the question, well, if I keep going, at what height above the surface would I extrapolate out to zero? Right? I have some rate of change right at the surface. I can calculate the slope, the rate of change as I'm at the surface. If I just fix that rate of change and keep moving upwards another distance z, at some point I'll hit a zero. So where's that going to be? Well, I know what the derivative with respect to the surface normal is. So if I just take that value, du dn, and I multiply it by some extra height, a distance above the origin, z sub b, b for boundary. So now I multiply a rate of change with respect to distance by a distance. If that amount equals the value at the boundary, then at that extrapolated height, I will now have a value of 0. So if I just make this equal, if I just substitute in for what du dn is, that's going to give me z boundary times this quantity over here. I'm only interested in its absolute value. So the absolute value of that is Cn over 2AD. And then I plug in the u that I have here. Right, so I multiply both sides of this equation by zb. So what I've got now is I've multiplied zb by both sides of this equation. And I found out that zb times the rate of change at the boundary, and I'm looking for when that's actually equal to u itself. Well, if this is equal to this, I can cancel out the two u's. They cancel, and I get that this quantity here must equal 1, and that leads to a value of the extrapolated boundary equaling 2AD over Cn. The diffusion coefficient is equal to Cn over mu s prime, and the limit where mu s prime is much bigger than mu a, which is a good approximation for diffusive tissue, except that I forgot the value of 3 there. And so this is equal to 2a over 3 us prime. That is a length, because mu s prime is an inverse length and a is dimensionless. So now I have the height of this extrapolated boundary. So how do I use this extrapolated boundary to solve an actual problem? As we've seen in class, if we have a tissue, so here again is the air, and here's the tissue. If I send a laser beam into this tissue from above, we've approximated that that's like creating a light source one scattering length below the surface. We're going to make the gross approximation that all of those photons scatter exactly one mean free path for scattering below the surface of the tissue. So if I mark that out for you, I'm saying that this height here, I'm going to call that Z0, the depth of the source inside of the tissue, and that's equal to 1 over the reduced scattering length. Now I can calculate using my infinite geometry solution for what energy density would be caused if this were in an infinite tissue, but it's not in an infinite tissue. We have a boundary condition. And the boundary condition is that it's some other height up here, this height, which is what we've called Z sub b, we need for the energy distribution U to equal 0. So with this location, U equals 0. How can we arrange if we had an infinite tissue everywhere here, how could we match this condition? How could we, if we have a point source here in an infinite tissue, where else could we put a point source such that U would be 0 everywhere on this boundary? And the answer is to do a mirror reflection, go from the source to the boundary double that so that it's symmetric across the boundary, and put an image source here. And I'm going to draw it as an open circle. And the reason it's an open circle is because this is going to be a source of negative photons. So if down here at the bottom, I have a power P naught, here I have a power negative P naught. Now that doesn't make any physical sense. You can't actually have negative photons, but mathematically we can do this, and that works out to be okay. So if I have positive photons coming from here, negative photons coming from here, then anywhere on this boundary, the sum of those two contributions, since they're equal distances away, the sum of those two energy densities will come out to 0. So I've satisfied my boundary on this extrapolated boundary. That's what this thing here is called, the extrapolated boundary. This is the extrapolated boundary. And the height up to this point here, that height above the bottom here is Z naught plus 2ZB. Because this is Z naught plus ZB, so this is Z naught plus another ZB. All right, we've now got our geometry. We're basically done. If we want to know what the energy density is anywhere in this tissue, I just have to calculate this distance, R1, and this distance, R2, and add up their solutions for the infinite geometry solution, which we already have seen in a previous tutorial. So let me emphasize that again. So this geometry allows us to calculate U total of any location in the tissue. All we have to do is say that the energy density at any cylindrical location rho and any depth z into the tissue less than or equal to 0, so within the tissue region, that is just equal to the energy distribution that we would get in an infinite geometry for the point source that's in the tissue plus the energy distribution that you would get if you were inside of an infinite tissue geometry for the negative point source that is above the tissue. And that's a really powerful mathematical physical assertion here. It isn't in fact the case that there's tissue everywhere here, but within the tissue region, you can pretend that there's actually no air above you and add up the contributions from 2 point sources, one positive, one negative, at different distances from where you are. And the sum of those two things will give you the energy density at that location in the tissue. And that becomes a powerful tool if we want to calculate the light that's being reflected out of the tissue and into the air.